Okay? Yeah. First of all, I would like to thank the organizers for not starting the event before 11 a.m. I think that's very nice. And of course, for choosing this incredibly cool location. So this will increase my nerd factor a lot, giving a keynote talk here at C-Base. And of course, I would like to thank generally that we have this workshop at all and that we get together here. So what I'm going to do is, the talk is essentially composed of 3 parts. So we have, I was informed that we have actually some people who are complete ML newbies, so I'm going to give a quick introduction to ML in general. And then the core of the talk will be a tutorial on kernel methods. And this will be quite technical. So after that, I'm going to show you what we can do with it. And of course, I'm using Shogun for the experiments. So that will be the last part on multiple kernel learning, which is mostly from my PhD thesis. So first of all, hello Wikipedia, what is actually learning? Learning is the act of acquiring new knowledge, behaviors, skills, values, or preferences, and may involve synthesizing different types of information. Furthermore, the ability to learn is possessed by humans, animals, and some machines. Learning may be viewed as a process rather than a collection of factual and procedural knowledge. And it continues, learning produces changes in the organism, and the changes produced are relatively permanent. And I just included the last one for the neuroscience geeks here, not looking at particular people. Okay, so there are 2 things I want to emphasize here. So the first thing is we care about machines learning, right, in this talk and then at this workshop. And the other thing is, which is I think is very important in machine learning, it's actually at the core of machine learning, that is synthesizing different types of information, right? And this is much in contrast to what you usually do in computer science, when you come up, you know, with a rule of, you know, if the temperature is higher than this, then turn off the machine or something like this. In machine learning, we use different types of information, and every type of information adds a little bit of evidence for the final decision of the learning machine. So, what are actually the origins of machine learning? Well, there's this game, checkers. It's maybe not as complex and exciting as chess, but I guess all of us used to play this as kids. Checkers is a strategy board game, and there is a vivid history of actually computer checkers, actually. So in 1952, the first computer checkers game appeared. So computer checkers, that is like computer chess, like Deep Blue and stuff, but for checkers, and it's much older, of course. So actually this was one of the first computer games. Yeah, so very early ancestor of World of Warcraft. And this was developed by the famous computer scientist Arthur Samuel of Stanford University. And some of the unique features were, so first of all, the alpha-beta algorithm, which is now in every computer science textbook. At that time, it was a seminal breakthrough. And the other thing is the intelligent adaptation to the opponent's strategy. So this is, of course, this is the origin of machine learning, essentially. But this program actually didn't have any chance against human competitors. So, I don't know, but it has improved over the years. So now humans have, of course, no chance against computer checkers programs. I mean, they don't have even a chance against computer chess programs, right? So this Arthur Samuel actually defined machine learning. So he said, this is a field of study that gives computers the ability to learn from data without being explicitly programmed. So this from data is something I added here for clarity. And, okay, so, and there are some, so eat this at this point, because now I'm changing to what can we actually do with machine learning. And of course, we can do a lot with machine learning. There's a big hype on machine learning and big data and all kinds of application fields in the information age. So one classical example is, of course, robot learning, making robots to learn better, navigate better based on roaming their environment. Or another thing is, which is in the news everywhere right now, data mining of electronic health records. Right, if you have huge university hospitals, they collect so many doctors' reports that you can actually mine information from them, and this hasn't been done traditionally for a very long time. Only recently people came up with this. And another geeky example is actually, look at this to the right, this HTTP request. And so one interesting thing, and that is also very much implemented into Shogun, is actually the anomaly detection. Detecting anomalous behavior in computer networks or the internet. Right, and this is something where Shogun is actually perfectly suited, because we have very efficient string representations there. And another thing, and the same can be said for this, computational biology, in particular genetics, where you aim at developing statistical learning algorithms that learn to detect more and more key positions in the genome. So, formally, in the easiest formulation, the simplest formulation of machine learning is we aim at writing computer programs that use data instances xi and their respective annotations yi. And in the simplest case, I assume that those are vectors and binary values respectively, and they are called training data, to compute a function that predicts, if you get a new data instance, the correct annotation. So this is the formal setup, and for instance, if you, in the IDS example, we would learn source code from source code or network traffic xi to discriminate benign code from malicious code. So let's take a look at the something that when I get, so let's say a colleague gives me some data. So the first thing I do is I try out this algorithm. It's if you know nothing about machine learning, this is the first thing you will learn. The k-nearest neighbor algorithm. Given an input, you predict the label f by majority vote over the k-nearest neighbor of the training data. So for instance, if you choose k equals 3 nearest neighbors, so this greenish point here in the middle would get a red label for k equals 3, and for k equals 5, a blue one. So it just checks the neighborhood and performs a majority vote. And it's of course implemented in Shogun, but you can implement it also yourself, I think. So this algorithm actually performs surprisingly well. So if you never use it, actually it gives a quite nice baseline to start with a data set of which you know nothing. So there are, of course, much more sophisticated algorithms, and I could somewhere already mentioned by Heiko, so let me make this really briefly. So for instance, there's an area of machine learning called probabilistic machine learning, where you model the inputs and labels by random variables, and then you just essentially try to predict the label that is the most likely for the given data instance. Another areas of machine learning include, for instance, kernel-based learning. This is something I'm going to talk about more closely now, but there are many more, like tree-based learning, neural networks, and they have their particular advantages and disadvantages. There's not something like the best bunch of methods. So for instance, tree-based learning methods, they can be very efficient and used for very large data sets, like 100 million data instances and stuff, where you maybe cannot use an SVM anymore. So, but yeah, so the message here is there are many different kind of methods. And I'm going to go deeper into now the field of kernel-based machine learning, so the core of my talk will be introducing this field. So essentially, kernel-based machine learning is an efficient way to carry out linear algorithms in some high-dimensional space. The core idea is here that linear learning algorithms can be much more expressive in higher dimensions. So, for instance, let's say you have some two-dimensional data here on the board. So this is our data. We have the axis and we have the circles. And you would like to get such an description. So what you can do is, if you map the data using this mapping into a three-dimensional space, it actually looks like this. So you can, if you would plot this on your computer, you would get this picture. And of course, this is we can have a linear separation. So you think of this as the data, you have brought it in such a representation, but this representation is maybe not optimal for linear algorithms, but you could, change the representation. For instance, I could use polar coordinates here, and I wouldn't have any problems using linear algorithms. So, like, kernel-based machine learning is a way to do this very principle, finding a good coordinate system. It does this. So, essentially, it would be the following three steps. You project the data into a higher dimensional space where it can be linearly separated, perform the separation there, and then this corresponds to a nonlinear separation in the original space. Now, there's a problem with this. So the problem is that the computation of scalar products in high dimensional spaces will not be efficient. So let's say the dimensionality of the space is 1 trillion. Well, if you have an array of 1 trillion numbers, well, that maybe will not fit into your computer's memory. So therefore, machine learning people came up with a trick. And this trick is called kernel trick. And its essence is to carry out this mapping just implicitly. And it works essentially like this. Let's say we have two input points given, x and x tilde. And let's say we use the mapping from the page before, then actually we get this scalar product in the feature space. Now, if you do your homework now and compute out this, do the multiplication here, it leads to this, right? This times this, and then plus this times this, and so on. So you get this. And if you look at this more closely, this is actually nothing but the scalar product followed by a power of 2. Now, if you look at this, so this is much simpler now, because using the inner product in the original space, well, that's the low-dimensional space. There we can compute those inner products. And then we just do a very simple numeric function after that. So this is very efficient. And the idea is we call this product here the kernel. And the kernel trick is just the following. We can kernelize a learning algorithm by substituting all occurrences of the scalar products in the high-dimensional space just by the evaluation of the kernel function. So this is just the whole trick. So are there questions actually at this point? So, and more generally, so what I showed you, that's a kernel. But actually, it turns out there are a lot of kernels. Like there are Fedora kernels and Gen 2 kernels and whatever. I don't know. Huh?
Cashew kernels.
So the same is also in machine learning. There are a lot of kernels, and of course, so maybe I think there are some Chaos Computer Club guys also joined. So kernel doesn't mean here the Linux kernel. This is a different context. So the kernel in machine learning, it's defined formally like this. You can call a symmetric function of this form a kernel if there exists a map into a high-dimensional vector space. Yeah, mathematicians would say a Hilbert space, such that actually the kernel computes the inner product in that space. Well, that's all. So the bottom line is kernels compute inner products in some vector spaces. Yeah? So a Hilbert space is nothing but a vector space with a nice inner product. Okay? So, in particular, one can show that. So, actually, what you usually would use in the end are the following two kernels. So, actually, usually you would use the Gaussian RBF kernel. So, I would say, in more than 90% of the cases, Shogun users would use Gaussian kernels if they have numerical features. But you could also use the polynomial kernel, and of course that is also implemented in Shogun. So essentially what this does is it takes the difference between 2 points and then smooths it by processing it through an exponential function. So it makes the distances actually non-Euclidean. Okay? So that's the interpretation. Are there questions at this point about kernels? Because this is very important now.
You have another joke lined up afterwards?
Fun?
You have another joke lined up afterwards? If you ask questions, then you can make the joke. I'm waiting for that.
No. No, I really would like to know whether there is some feedback, or so that we can get some interaction going on.
So what you just said, the distance are not Euclidean anymore?
Yeah. So this is a squared Euclidean distance. So Euclidean distance is nothing but the a distance that comes from the standard scalar product in RD. Yeah. So it's the usual thing that we know when we think of a distance. That's the first thing we think of. So, however, this transforms it into a completely different measure, because if you process it through an exponential function, and we all know the exponential function, it does something like, if there's a very large value, it will become much larger. If there's a very small value, it will become much smaller. So it makes the effects even more stronger. So if you have a large distance here, the exponential makes the distance much larger. Or the similarity equivalently, which is captured by the kernel, much smaller. Yeah? So this leads to actually viewing your data in neighborhoods, in local neighborhoods, which is pretty similar to our simple example from the beginning, the k-nearest neighbor algorithm. More questions about this?
Would any norm work there, or?
Yeah, sure. You could use other norms. Yeah. Actually, I think you can use any norm.
What is the Hilbert space?
A Hilbert space is just a buzzword like big data used by machine learners, especially guys who work on kernel methods, to describe a high-dimensional Euclidean space. Okay, so Euclidean space means something like an array with numbers. Okay, just the usual vector space we think of, like we learn it in school. Okay, so if you make this vector larger and larger and larger and let it go to infinity, you get essentially a sequence, because it never ends. Imagine you would, again, you would add numbers into the vector. It grows and grows and grows and grows. Yeah? So imagine you have this infinitely long vector. It's not anymore a Euclidean vector, but it lives in a Hilbert space. So Hilbert space is just a word to describe a generalization and extension of what we think of vectors. Right? It's more abstract. It's like an infinitely long vectors, and together with a way of measuring the similarity of vectors by a scalar product.
So it's somehow like an infinite dimensional space.
It can be, yeah. Yep.
It can be, or it is.
It's more general than a Euclidean space. So in particular, the usual space that you usually think of, the finite dimensional, it's also a Hilbert space, but you don't need the buzzword for that. It's like using big data methods for small data. More questions? So the next important notion is the one of the kernel matrix. So the kernel matrix is just the matrix that is decomposed of the kernel evaluations of pairs of input points. So if you have a bunch of data, let's say 1,000 points, the kernel matrix will be 1,000 by 1,000. It's just measuring the similarity of every pair of points. Okay? So this quantity is this is quite useful because it gives us another characterization of kernels. Because one can show that a function, a symmetric function is a kernel if for any n input points, and n can be any number, the kernel matrix is positive. Yeah? Now we know what a positive number is. 1 is a positive number, minus 1 is a negative number. But to say what a matrix positive is, well, this is something we learn in linear algebra. It's a generalization, and you measure positiveness by this positive semi-definiteness. Okay? This is something like saying it's greater or equal 0. So imagine that that you have come up with a kernel and you want to show, or you want to check, is this really a kernel or not? Then theoretically you would have to check all kernel matrices that you could derive from any data, and if they would always be positive semi-definite, then it's a kernel. But of course this is just theory, because we cannot try out any data set in the world. Actually, we have to try out any data set that could exist in the world, not only any that is there, right? But I tell you something, we have implemented kernels in Shogun, of which we don't know that they are kernels. And especially there is one kernel which was implemented into Shogun, I think, in 2001. The weighted degree kernel, I think, was this. And in 2010 or something, someone proved it's a kernel. But we have been using it for a decade, and it never turned out to not be a kernel, right? So if your kernel matrix turns out to be positive for any data set you try, well, who cares about whether it's really a kernel or not? Yeah, so it's fair enough in practice. Yeah?
Yeah, so what happens if it's not positive simulated?
Well, you will end up in a big trouble. So Shogun will give you an exception, I think, and say, don't, around with me.
What's the problem? So what's happening in the solution?
So the problem is that if the kernel is negative, then you cannot guarantee that such a mapping exists into a high-dimensional space. So first of all, it's not motivated anymore properly. But maybe, okay, let's say, anyway, we could try it. Yeah. So the next thing that happens is you get serious numerical problems. Because the usual algorithm that you would use, like regression algorithms or classification algorithms like support vector machines, they will not converge to the optimal solution anymore. They can do weird things like circling around and not finding a good solution. But you know what? In practice, you could still deal with this stuff, but it's it gets a little bit esoteric at this point if the kernel is not positive enough. So I'm not sure what Shogun. I think it will just throw an exception or do weird things. I'm not sure.
I mean, lots of times you want to do certain, say, decompositions of this matrix. You want to compose it into like a Cholesky factorization, say, and this doesn't work. This doesn't. Any algorithm for doing this will tell you I can't do it because the matrix is not positive.
Okay.
So we'll just break. Yeah, all these SVM solvers, they're all like you said, the problem they're solving is not well defined anymore. So I just mix up and all these algorithms text for this. So they'll tell you I can't do this.
But I think it's important to mention here, there is a trick of the trade here. There is a trick to actually make this matrix positive. So if it's actually not positive, what you can do is you can add a positive matrix on top of that, like a multitude of an identity matrix, for instance, and it will become positive if you add enough positivity on top of the matrix. It's a trick, but people do it.
That doesn't really convince me. I mean, if you have a negative adaptive kernel, I mean that's like a ball shaped down, right?
Yeah.
I mean, you can add any positive number and it still be negative at some point.
No. Actually, the kernel matrix, if you would compute the eigenvalues. Let's say there's one negative eigenvalue. Yeah? Then you just need to add a sufficiently large identity matrix, multitude of an identity matrix, and this negative eigenvalue, it will actually at some point be 0 or larger, the more you add, and the matrix will eventually become positive. Like imagine I would have a matrix, a kernel matrix, and the entries are between 0 and 1. And now I add a matrix that has a diagonal with entries 1 trillion everywhere and 0 offside the diagonal. So I guarantee you this matrix is positive.
Maybe.
Okay.
But wouldn't you still
Yeah.
get into trouble if you encounter new data and you try to classify it with the kernel that is, not with a kernel?
Yeah. It might or might not. It depends. It could actually help even. Yeah.
Repeat the question.
Oh, okay. So the question was, if I use this dirty trick I just proposed of adding a sufficiently large multitude of an identity matrix of a negative kernel matrix, then could this lead into some trouble, like not capturing the data well? And the answer is, of course, yes, it could lead to some trouble. But it could actually make things better, because we know for some kernel algorithms, actually adding a multitude of the diagonal matrix acts as a regularizer and can actually help. the problem. So the answer is yes or no. It's not. It depends on the data, as always. So an important question is, when can a learning algorithm be kernelized? So, for instance, can k nearest neighbor be kernelized? Who thinks yes? Who thinks no? Okay, again, let's do this again. Who thinks yes, k nearest neighbor can be kernelized? Who thinks no? Okay, so some people think no. So, in fact, k nearest neighbor just depends on distances. So it turns out you can, like measuring distances, square distances can be expressed by measuring scalar products. And scalar products, they itself can be substituted by the kernel function. So the answer would be yes, the correct answer. Actually, almost any algorithm that is just, or any algorithm that is just based on square distances between data points can be kernelized, in particular k nearest neighbor, k means, and anything. Okay? So the general criterion to ask when can my kernel algorithm be kernelized is if the training and prediction steps can be solely expressed through the kernel. I mean, the dependence on the data must just come through the kernel. Yeah? So for example, let me give you an example, the support vector machine. It looks like this. It solves this quadratic convex optimization problem. And obviously we see here, there's no point here where the data enters. We have here the variables alpha, we do some maximization, we have the labels here. The only point where the data enters is here via the kernel matrix. So this algorithm trivially can be kernelized. We can see it, it's already there. There's just a matrix, okay? So, but more generally, you have to ask, can we reformulate my algorithm such that the algorithm depends on the data only via evaluation of kernel functions or the kernel matrix? And then we are fine. And like I said, in many cases this works. The same is with the prediction function, actually the linear prediction function. We can show that this W parameter vector of the function can be expressed by a linear combination over the input points mapped into the high dimensional space. And if we substitute this back, we get this expression, and it just depends on the data via the kernel, so we are fine. Questions about this? So more generally, there's the following we can do. So the question is, does this work also for other algorithms as SVMs? And the answer is, of course, yes. For instance, for ridge regression, it does also work. And generally, there's a very nice theorem that says if we have a kernel and a strictly increasing function on the quadratic norm of the parameter vector plus a loss function, then any solution of this problem admits a representation such that the parameter vector is in the span of the data in feature space, in the high dimensional space. And this is very nice because if we have this representation, we can use the trick from the previous page to plug this into the this linear prediction function here, and we get something similar to this. So an expression that only depends on kernels. So this is really nice. This gives us a very general theorem. So if, let's say you have come up with a new algorithm, you say, okay, so I have a new algorithm, and I think it can be kernelized, but I'm not sure. You can check this criterion and write into your paper, okay, a theorem follows from this theorem. My algorithm can be actually expressed as a kernel algorithm. Good. So actually, this was. So I'm actually already through with the technical part of the tutorial. Yeah. So let's get to a more Shogun kind of and what can we do with this actually part. So for further reading on the methods, I would suggest this review paper. Yeah. So next I'm gonna talk about. I'm giving a quick glance on multiple kernel learning. So multiple kernel learning is an extension of kernel learning, and in particular I've been working on this since many years, and I could show you some nice pictures and stuff of applications, and the experiments have been performed with Shogun, and you're gonna love this. So so the problem setting and this multiple kernel learning is that you have multiple kernels, right? So rather than having the data and going into one dimension, into a single high-dimensional space, you have multiple such mappings. So imagine, for instance, you have a kernel capturing the color of images, another kernel capturing the shapes of the images, another kernel capturing the tilings of the image, and so on. And the question is, in multiple kernel learning, how can we combine these views in an efficient way? And one answer is, or let's say one problem is, color is maybe not always useful. Just focusing on one particular representation is not always enough. So in multiple kernel learning, the approach is to use ratings of these feature spaces, or equivalent of the kernels. And so one approach that has been used for a long time is using sparse weights for this approach. This sparse means here that kernels, or equivalently these views, are completely switched off, like the color kernel is switched off or the shape kernel is switched off, something like this. And a philosophical question here is why actually? So this has actually historical reasons, because originally the multiple kernel learning was in a formulation that it automatically led to sparse weights, and it was actually not clear. It just was like this. Okay, it was not clear whether something would exist that leads to not so sparse weights. But I'm going to show you this. It's a really easy one, I think. So do you see what it is? Okay. So this is Berlin's favorite morning drink. Then I'd say the afternoon drink is then a beer and club mate or something, or an evening drink. So this you would typically drink when you meet with your friends in the morning. Yeah? We call it Milchkaffee in Berlin. So back to this sparsity issue. So actually what was really happening for some time in multiple kernel learning, and makes me laugh when I think back to these days, is that people used to study this sparse method very intensively, but it was kind of strange that all the papers focusing on this were just focusing on the optimization of the learning problem, on speed, numerical aspects. And I will show you later how we improved these by a factor of 100 with Shogun. But the point is that actually there were no papers really evaluating this empirically. So people were just, writing papers, how can we make this faster? But there was no evidence whether it's actually useful. And at some point, we began this in 2008 at NIPS. We had a talk on this issue, saying something like, look, this is actually not working. And there were actually multiple talks on this subject in the first workshop on MKL at NIPS. And I've been working on actually taking this to a non-sparse and more effective level that can actually be used in practice. And of course, this is like a typical outline of what you do in machine learning research, right? There are usually these 3 levels. You can do your math homework on one end. You can come up with new algorithms, and then the most important thing in the end, I think, is whether this actually works in practice. And this is something that has been a little bit forgotten in the early days of multiple kernel learning. So essentially, the idea of this non-sparse multiple kernel learning is well, first of all, you parameterize the kernel as a linear combination of the base kernels. Like K1 is the color kernel, let's say this is the shape kernel, and so on. And you give some positive weights. But you would like to compute these weights also, right? So one thing that you would not want to do is like perform a grid search over those weights or stuff, because this will take like forever to find a good solution. So actually, it's so simple. Now, when I look back to this, it's so simple to do this, but you know, it's one of the things where you just need to have the right idea, and then it looks so simple. So the idea is just to actually optimize also over those weights. You just integrate the optimization of the weights into the optimization problem, because something like the SVM, it's an optimization problem anyway. So you just, you know, add another variable, and that's it. But you need to also add a constraint, otherwise you will end up with kernels with just infinite entries, which we would not want. And turns out this is an easy problem. It's just convex, like an SVM. It's really easy. And we can now use, because it's very general, also very general norms like P norms, and if we use a P equals 1 norm here, then this will lead to a sparse method. But if we use, shown here on the left, but if we use another norm like the usual P equals 2 Euclidean norm, then we get actually here non-sparse solutions. So shall I explain this image or this picture? Or so what is shown here is just, these are the level sets of the objective function of this problem. And we can see that the optimum is there where it will hit with the constraint, because we need the constraint to be fulfilled. And it happens that it will be on the edge or offside the edge of the constraint set, depending on which parameter you choose. Now, you can do now a lot of math and stuff with these things. I'm not going deep into this. I just wanted to show, because when you do this machine learning analysis, you have usually these 3 steps, and I just wanted to, that's the reason why I wanted to show this. So I'm now coming to the most interesting part, and that is our Shogun implementation. So we have implemented 3 different algorithms solving this problem into Shogun. So the simplest one, if you use this in Shogun, you will see there are a lot of solvers you can choose. So essentially it's these 3. So the easiest solver that doesn't require an optimization toolbox is actually this simple EM kind of algorithm that optimizes an SVM and afterwards the kernel weights by an analytic simple formula. So actually we first implemented these 2 because this is how science is, right? We first found actually this method, then we found this method, and we had them implemented and we used them, and then we had the idea for this method. And this is actually this is the most sexy one. It's so simple, and it's you don't need an optimization toolbox, so you can use it especially well for, you know, non-commercially, and so and this probably works also. So of course we have implemented this in Shogun, and it combines very well with, you know, the modular design of Shogun. So we can use, and we do use actually string kernels, for large DNA data and all this stuff together with this learning algorithm. And I have told you, so people were writing papers on how to better optimize this not so well working, actually this original version of multiple kernel learning. So we never understood how they could actually publish these papers, because all those methods, they were incredibly slow, because they were just implemented into MATLAB. Now you can imagine if you implement an optimization method that performs 10,000 or 1 million iterations or something into MATLAB, it will not be fast, right? So we implemented this, of course, into Shogun, and it's about 2 orders of magnitude faster than the previous approaches. And it works. Huh? Pardon?
So is this speed up speed up only due to this implementation, or also due to the algorithm?
So the question was whether the speed up comes mainly from the C implementation or from the algorithm. So of course, most of the speed up in the end comes from the implementation, because it's just incredibly efficient, you know, to implement stuff into Shogun. Okay, it's like this. So it's not about the algorithm; it's really about the toolbox. And the really funny thing about this is, usually when you work on a new algorithm, you either try to be faster or more accurate than previous baselines. So this is, I think, the only example I have ever seen in my life where both actually came true. So this is a particular example of computer vision, where imagine the following motivation. Let's say you would try a image search in for instance, in Google, and you would type in the name dog. Then what you will get is actually pictures of dogs. Okay, but what Google actually does, or at least did, up to my last knowledge, right, is to actually scan the web page content for the occurrence of the word dog, or more generally for a topic model, some model to analyze, you know, the content of the web page, rather than analyzing actually the content of the image. Okay, so this was actually, but also, I mean, analyzing the content of the image. I know it was in beta stage. I'm not sure, maybe it's now already running in the core search engine of Google, but anyway, so what we do here is finding actually really objects in images. Okay? So this has a very strong motivation. It's very useful for search engines. And we actually generate a couple of kernels from images, you know, capturing the color distribution, capturing the shapes of the images and local features. You know, you try to find key words in the image, key points in the image, and all these kind of things lead to a bunch of kernels. And now we can apply our method to this setting, and actually we did this, and together with my colleague Alexander Binder et al. And he's really a core developer, or semi-core developer of Google. Here's in the inner stage, I'd say. So we have performed these experiments in Shogun, and it actually turned out to work really, really well. So well that we actually won a image recognition challenge with this method. Although I have to say, of course, it involves a couple of more hacks. But this is one of the hacks. So, and now I want to show you another last very interesting application, because this is really an application where the modular design of Shogun comes into the game. So I mean, here it comes into the game as well because we use multitask SVMs here, right? But here we have this very interesting genetics application where the aim is essentially to find genes within the genome, right? Genes, these are positions in this super long genome that encodes all the information that, you know, leads to us having green or blue eyes and all these kind of things. So genes are the positions that are interesting in the genome because more than 99% of the genome is just crap, please excuse me the word. So the interesting locations are really just so essentially there's just noise and not interesting stuff in the genome and only a very small, okay, he's laughing. Pardon?
I disagree.
Huh?
It's okay though, for the purpose of the talk it's fine.
Yeah.
For instance, if you take big groups of people who have diseases and you look for the mutations that they have in common, some, maybe only 5% or less of them follow genes. So there are a lot of very, very important regions outside of the genes that are important to disease. So.
Okay, so there was a comment that in some cases, actually even regions that are outside of the gene can be very important. And of course this is true because this is just a simplified description because there are other factors in the gene that interact with the process, the gene is translated and so on. You know, if you dig deeper into biology, one thing that I learned is whatever you tell people, it's not correct. Someone else will come and say, no, it's not true. It's too simplified model. The true underlying, I mean, what is truly underlying is more complex. It's really insanely complex, right? Okay, but in a simplified description, the genes are the things we are looking for in the DNA, and one particular interesting position is the start of the gene, the TSS. And we have tried to find these gene starts by using various feature representations. So the first one is, for instance, just looking on the strings associated with the DNA, right? Because DNA looks like it's composed of 4 nucleotides, and you can represent it as a string over an alphabet with 4 characters. So we just look on the raw strings, and this gives us the first kernel. Another thing is we can look on the distribution of these nucleotides, like just counting. How often do we have an A? How often do we have an C? And so on. And another thing are really higher order factors of the DNA, like how, you know, the DNA binds in this region and these kind of things. How much is the DNA twisted in a region? And so the empirical analysis comes with a challenge here because these data sets are really large. And however, the nice thing is in Shogun we have this incredibly nice and efficient string kernel implementations. Yeah, and this is what really saved our here. So, so the bottom line is that we were able to perform this experiment despite the computational challenge, and we found actually that the using the new method is actually slightly better than using the old methods. And this is, I think, very nice because the old method actually is already the winner of a comparison of 19 models. So if you are a little bit better than that, that's not too easy to be. Questions about? Yeah.
So is there in this case any difference between using kernels on these sequences and
Pardon?
Is there a difference between kernels on these sequences and explicit representations? Do you just make like dot products between these encodings?
So the question was, is there a difference between using kernels and for this experiment, or using explicit representations like vectors, right?
Usually, like is this feature space that you're in, is it kind of, do you know what it is? Is it finite? And
it's finite and incredibly large. So if you take, for instance, the weighted degree kernel, it gives rise to a extremely high dimensional feature space. So you would not work with that directly. It's in the order of 10 to a large exponent many features. So, yep.
How do you find the right P for your P norm?
We just try it out. We just, it's just one parameter, right? Just a scalar quantity. We just try out a couple of values. And within our model selection procedure, take the one that works best.
Is that actually discounted in these graphs, that you have a more complex model? I mean, it's like the one norm MKL just has like the parameters fixed, and for the rest you have like a span of values you can actually search for optimization.
Can you say that again?
Are these graphs discounted in terms of that you have...
Discounted?
Yeah, like you penalize that you have one more parameter in comparison to the one norm in KL. Because you can optimize over the P value, right? In terms of how you define your norm.
You mean when we compare the runtime, or?
The performance and the runtime.
Well, the performance is not a problem because we choose it in model selection. So this is all safe and stuff. But of course you have to take this additional loop, let's say trying out maybe 4 or 5 values. That's completely sufficient. Actually 3 or 4, it's more than enough. Okay. It will take you, it will take a little bit longer, but you know the gain is great. I mean, the implementation, the Shogun implementation is so fast we can do it. Okay, that's the bottom line. More questions on this? So you can actually, try out more data sets using Shogun on this method, and and it will give you different results. So for instance, actually we've found a data set for which the sparse method, the original method, works best. So up to my knowledge, up to today, this is the only data set someone ever found where this original method works best. Okay. So anyway, so it depends on the geometry of your data, which whether the data is too sparse or not too sparse. Yeah.
So I was just wondering, for this case where P equals 1 works best, is there an interpretation in terms of
yes.
features?
There are many kernels in that set that suck.
Yes, but is there a scientific interpretation of why this happens and what features are actually relevant and what are irrelevant? Is this sparse?
Yes, yes. And there are several features in that set. There are several kernels in that set, of which you could have known that they are not so useful, but were included into the experiment. Maybe also for the sake, of getting this outcome, and that really hurt performance if you include them into the set. But here's something I want to tell you. So from my experience, if you have a bunch of kernels, a baseline that works really nice is you just add up the kernels and run whatever method you use, kernel-rich regression, support vector machine, k-nearest neighbor, whatever. So adding kernels to your set, adding information to your learning problem, by for instance just adding all kernel matrices, does not hurt you as much as excluding information. So if you are not sure and you have a choice, just add up a bunch of kernels and run an SVM. It's easy and works pretty well. But since we are using Shogun, we can also use this, you know. Okay, so that's it, and I think this explains. I think this is a nice end of the talk. It was quite, you know, technical in the beginning, but I'm happy that I could show you some pictures and, you know, Shogun running real well in practice. Okay? Yeah. Thank you for your attention, and if you have some questions. Mm-hmm.
So I was wondering that when you're adding all these kernels there, right, you're on the data that you also want to optimize. And usually people say that it's not a good idea where you're, I mean, it looks a little bit like model selection to me, where you're trying to add kernels or kernels. And now you're optimizing your weights as well, and you're also optimizing your linear combination of kernels with data as well in the same objective function. So why do you think this actually doesn't give you a problem in practice? Is it because you have these constraints?
Okay, so the question was, you know, you have this additional parameter, and I still cannot believe that there's something esoteric going on, that maybe there's some overfitting issue or these kind of things. So the reason why there is no problem with this from a methodological point of view is that it's just a joint method. You have one, you know, you take the data, you put it into a black box, and something comes out of this. Yeah. So it's the optimization over the P. It's included just in the convex learning problem. There is no magic going on, like, you know, non-convexity or something. We are not, you know, tuning a million parameters in model selection, like in deep learning, and overfitting completely to MNIST data or something like this. This is different. We are just solving a convex problem, and the convex problem has, instead of one parameter, which would be the soft margin, the regularization parameter, another parameter, and that is just the one for the norm. It has a very mild, you know, impact. It's still a very small set that you traverse in model selection.
Well, my problem is not that you have more parameters. The problem is that the way that they're being optimized, they're all optimized within one cost function. And usually you would run into problems if you try to set your hyperparameters in your parameter using the same
Okay, so the question was, it was a little bit clarified. So the concern was not on the evaluation of the method. The concern was rather, why does this actually work? Because we optimize over, you know, over a whole set of kernel weights. It's an infinitely large space. How can we, you know, how can it be that we don't overfit? And in fact, because we have a regularizer on the vector of the weights of the kernels, right? The weights of the kernels, if you write it into a vector, we just use the norm of that in the objective function of the problem as a regularizer. So it boils down, if you believe that regularization helps, for instance, SVMs or regression methods to perform better, to not overfit, the same can be said also to multiple kernel learning. Yeah? Further questions on machine learning, on kernel methods, on multiple kernel learning methods, and the way Shogun interacts with this? Yeah.
So most of the kernels I use are somewhat designed by hand, so I have an idea of like what features I should take into account.
Yeah.
Okay. How does it work? Like, I mean, it's like, are you an artist? It's like, yeah, maybe.
Yes.
Maybe this seems to be a right idea.
So the question was, are you an artist, or how can you, you know, be able to actually come up with set of kernels, describing the problem and these kind of things. And the answer is, of course, well, you will be only as good as you are able to find good representations for your data, or find people who can find good representation for their data, domain experts, biologists, or people like that, right? So if you don't capture the data properly with regard to what you would like to predict, well, then it won't work out well. Yeah. So this is the art rather than the science part of machine learning research.
So can you comment a little bit about optimizing kernels over parametric families? So tweak the bandwidth of the Gaussian kernel together with optimizing.
Okay, so the question was, can we take this to another level rather than considering picking a kernel from a family of kernels that is rather restrictively parameterized as a finite linear combination of some base kernels? Can we come up with the kernel completely from scratch? Making completely automizing actually machine learning or kernel-based learning. I mean, ideally you would like the machine to pick the kernel for you, and you would not like to have the biologist do that also. So this is of course as difficult as strong a strong AI. Okay, so it's of course a damn challenging problem. Okay, so what people have tried is solving easier problems like this, or solving something like just picking the bandwidth of the RBF kernel. And this is already a non-convex problem, but we can do it. Okay, we can do it. But and it's just one parameter, right? It's not really a difficult problem. But really engineering, having a machine engineering your features or your kernel, yeah, this would be my dream. But maybe it's probably only a dream.
From your experience, when you add this additional parameter, when you're also optimizing over bandwidth of
yeah, but it's only one parameter. It's not so challenging.
Does it actually help over these weighted linear combinations, or just like a grid of bandwidths?
We don't need it, because you just add. You can just add 10 Gaussian kernels with various widths or something like this. Actually, it turns out usually just using one Gaussian kernel is enough, actually. So this is rather effective. I mean, this is one of the reasons I was always laughing about these MKL papers, because in the empirical evaluation they often would do something like putting together a couple of RBF kernels with different values and trying how well, and then saying, oh, my algorithm works better than another one. So actually, from my experience, usually all methods perform equally well if you do this. Because if you really want to do this properly, you need, first of all, either kernels that are really complementary, like capturing completely different views of the data, like the string aspects of the DNA, the physical aspects like how do DNA bind at this location, the distribution of the nucleotides in a region, things that are really interesting and complementary that give you heterogeneous types of information, right? Or another thing is, you would use additional flexibility where in some spaces, parts of the input space, you allow the algorithm to pick different weights than in another part of the space. So this is something that is also very interesting. So have a look at my upcoming publications. Yeah.
So I think let's cut here because the pizza arrived.
Oh, okay.
So thanks again, Marius.
Thank you.